Let me zoom in on this if it'll let me. Okay, so what ends up happening is some friendly people, you know, the friendly calculus people, those guys, super nice guys. What they did with rate laws, right? We had talked about this right here, this first day. We looked at single reactants or products, and we just did the change in their concentration over time. This does not tell us the rate law for the entire reaction. It tells us the disappearance or appearance of one part of it, okay? So this is not a complete rate law, but it will tell us how fast something's appearing or disappearing, so that's helpful. Yesterday we looked and we made the whole rate law, and we looked at that as far as the orders of each of the reactants. We only put the reactants in the rate law. We calculated K by filling in things from that chart. We were able to look at the different reactants compared to the rate. The rate was determined experimentally. And then we were able to get the rate law. Today, integrated rate laws, that integrated stuff is coming from calculus, and that's fine. We don't have to know calculus. We really don't. Like, you have to know that an M&M looks like a 0. Seriously, it's hard that. So all they're going to have you to do on this is, you got a couple formulas to work with on your formula sheet. I'm going to show you this in a second. And then really, you know, they like to draw the circles, they like to draw the graphs. And what the graphs are going to draw is, if it makes a straight line, concentration versus time. So this is nothing but, let me get me, hang on, I gotta draw my capital M. So if I know it's going to be green. What color M&M y'all want today?
Purple.
Y'all want a red M&M? Purple ain't even a color M&M. That's a Skittle. That's a Skittle, my friend.
No.
Anyway, so if I put me a red M&M right here, if I had, see, that's molarity, but it's also an M&M. For a zero order reaction, the graph of concentration versus time is a straight line. Okay, so that what they're looking for is like, what makes a straight line? Doesn't matter what makes a curve. It doesn't matter about the curve lines. What makes a straight line? The one that makes a straight line is the order of the reaction. So if I got an M&M and it's making a straight line, M&M looks like a 0. How does it make you feel? I'm not kidding about how much this is on the test, on the real test, on the AP exam, on my test, all the tests. Okay, you might want to flip that packet over and just write this down, because it's not in there as clear as I'm making it. It's like hidden and tricky. You got a blank page on the back, right? You do. You can put it on the side. You can put it wherever you want. You put it on the back. But if you have a graph and it is molarity, which is concentration, versus time, and it's a straight line, this is zero order. And an M&M looks like a 0.
Are you saying 0 because of the brackets?
No, I'm saying that when you have a reactant and it is a zero order reactant, if you graph its concentration versus time, it gives a straight line. That's all I'm saying. And I'm just saying that an M&M looks like a 0, and that's going to help you remember it. Okay. How to know if something's zero order or not, that's kind of what we did yesterday. The rate has nothing to do with the concentration of that particular reactant. So the rate is going to keep being the rate, and it's going to make a straight line no matter what the concentration is. So your line's going to be straight when you graph it, because the reaction rate is just going to be based on, it's not going to be based on the molarity of this. It doesn't matter. So it's just going to make a straight line all by itself. How does it make you feel? If you saw a graph and it had in brackets an M, and it had, or a molarity, like 0.02 was a molarity, and it had that graph by time, could you say, okay, that's a zero order reaction? That's all you got to be able to do on this, for this part. So, there's that. When I look at concentration versus time for my first order reaction, first order reactions, you may want to listen to this next sentence. First order reactions are the same kind of graph as half-lives. Yeah, that looks like a half-life radioactive decay kind of thing. Okay, well, if I graph concentration versus time for that, it doesn't give me a straight line. It just looks like exponential decay. If I graph concentration versus time for a second order, it goes down, and it goes down even faster. So this, if I wanted to know something about K or the rate of the reaction, these curved lines are not as easy to use, and so that's where the calculus comes in. You don't have to know calculus, it's fine. Alright, so if I look right here, there we go. So concentration versus time on the zero order gives me this. I'm going to make this bigger. For first order, remember how the L on natural log looks like a 1? First order reactants, if I graph them versus time, I will have the natural log of them and then their molarity. Okay, so if you have a graph and it has the natural log of the concentration of reactant versus time and it makes a straight line, then that is the first order reactant. Okay, you remember that L looks like a 1? I wish to God that I had found this. Like, I made all this up, y'all, but I wish that I had, like, somehow magically taught myself this. Y'all are welcome in advance, because just for fun, if you just want to read through this part of your textbook, yeah, okay, yeah, never mind. So, if you're given a graph and it has the natural log of molarity in brackets and it's a straight line, it's first order. This is also about to come in handy when you look at those formulas that aren't identified on your paper. Okay, so that's first order. Second order, when I want that to be a straight line, it actually comes out to be a straight line if I plot 1 over the concentration, like your fraction on the way in the door. Okay? Second order, I'm going to have 1 over the molarity of the reactant. Got to write two things. Got to write a 1 and then something on the bottom. Second order reactions make a straight line when you plot their concentration with a 1 on the top. So but basically the inverse of the concentration gives you a straight line. How does that make you feel? If you can do that table thing from yesterday, and you can do this, you can answer the vast majority of questions on the AP exam. But I'm not kidding. So, there's that. Anybody got any questions? Can you remember that? Probably. Okay. You may want to, like I said, pay special attention to it, because I know I wrote your test, like I remember doing that before. I have like a vague recollection of doing that. So, now, just before we even get into the crazy integrated rate law stuff, look at your yellow sheet for me. Look at kinetics. There's a bunch of, like, natural log, 1 over whatever. So what's about to happen is I'm going to give you some numbers. And what you're going to do is you're going to have to find K. Now, if I have the rate, K is equal to the rate in zero order. I don't need a formula for that. Do you remember that? Well, if you're doing something, if it's a first order reaction, are you going to pick the 1 with 1 over A sub T, 1 over A sub 0? No, that's going to be for second order, you see? Yeah, and so the 1 with the natural logs, that's going to be for your first order. So that whole little formula sheet, you got it, everything's cool. The 0.693, that's coming up in this PowerPoint too, and I'll get to that. Let's have a moment of silence for making things a little bit easier than they probably should be. Alright, so find where we left off. And I'm going to get some courage up. Let me find it. It's right there. It's totally fine. Let me turn this little guy off real quick. Okay, so remember, guys, when we had done the rate of a single reactant, right, we had looked at the concentration over time and everything was fine. And that red sentence right there, it doesn't matter that they did this with calculus. Like I said, you don't have to know calculus. But it can be integrated with calculus to produce this. And what this is like dy and then dx. And then when you integrate it, like that's a real common integrated thing. And then this is the integrated form of it. And it just makes it a straight line, and then you can find the area under that straight line, and it can tell you how much reaction has progress at any point. You don't need to know that, though. You didn't know what I told you about an L looking like a 1, and there's the formula. That's all you need to know, okay? But I actually took the time to go talk to Miss Norris because I wanted to know what this meant, but it doesn't matter. But I think that's very interesting. Anyway, so, 0, little sub naught, that's what people will say. But the little 0 here, that's going to be your initial at a point 0 in time, and then T is for the final time. So, initial concentration at time 0 is A sub 0, and then A sub T here, or your concentration of T, is the concentration at some point in time. And this is the same little formula that's on your sheet, that will always be on your sheet, that you'll always get to use. Okay? So, if you can just keep it straight, that little L tells you that it's first order, then you'll be all right. You can rearrange this. Don't let this freak you out. All they did right here is they just they moved this on over. And they added it. See? I added it to both sides, moved it over, and then it makes a line, that straight line that I just showed you. That's all this is saying. So again, if you have the natural log of A, the concentration of A at any time, it'll make a straight line. And notice right here that the slope of this line is negative, and that K, that rate constant, has to be positive, and we want the rate to be positive as well. So just have a negative here, so it'll be positive. But we can all look at that and see that that's really a negative slope, right? But it just has a negative sign in front of it to make it positive. So, right here, they're not going to give, listen, don't freak out. They're not going to give you a data set without giving you that graph. You won't ever have to look at a data set and go, hey, that's first order. You can't eyeball this. They're going to give you that graph, and that little ticket of L looks like a 1 is going to get you in the door of knowing which formula you're about to pull off that sheet. Okay? So, anyway, here's some times, and here's some concentrations. I can look at this, and I can tell it's first order. To find the rate law for this, what I'm going to need to do, I think this is the one. Is this right around where I start scribbling stuff out, or do I have another second or two? Flip the page. Oh, I got a while before I get to the scribbles. When I get to the scribbles, y'all let me know, because they're making it way too hard. Okay, so the scribble one looks a lot like this one too. So I'm going to find the rate law. I got to find the rate constant. I know that the rate law, you don't even need to do anything to find the rate law. What's my only reactance right here? A. Okay, so I know my rate law. It's just going to have A and some brackets, and I do need to know the order for it. Can I already tell the order for A? This one. So the rate law, well, Lord, it's just right here. That's it, ain't it? That's it. Piece of cake. I didn't mean to have that up there. That was just coincidence, but I believe that's it. So anyway, there's the rate law. We know that it's a straight line, so it's just going to be first order. That's just, I had that from yesterday. So that's piece of cake, right? Your rate law only contains reactants. You only had one reactant, and it made a straight line. So, check. We're good there. If we're going to find K, we're about to use that formula that's on your formula sheet. And they're using T0 and some other time. You can go back to this chart right here, and you can pick 0 seconds and 50 seconds, 100 seconds. It doesn't matter. You can pick any of them. Because you know why? Because it's a straight line, right? So it doesn't matter. So there's that. Don't let this freak you out. Stop doing the thing where the letters make you scared. This is the formula on your formula sheet. Yeah? And what they have picked here, it looks like they picked 50 seconds. They picked 50 seconds. And so at 50 seconds, the concentration was at 0.017. I don't have the chart in front of me. Final mass initial should be. Was the concentration at 50 seconds this? And the concentration at 0 was this. and then you divide it by the change in time, which was 50 seconds. Now, we need to stop right here, and y'all need to get your calculator out to make sure you can work your calculator. So, to find the concentration of A at 500 seconds, you're still going to use the data at time equals 0. And so, all that stuff is the same. But what you don't know, your natural log of 500, or the concentration at 500 seconds, we don't know that. So same kind of stuff though. Is 500 seconds in the little data chart? Is it in the chart? Did it go to 500 seconds?
I didn't know.
I didn't think it did. Well, that's okay. That's what I was trying to say before we started. You don't really need to be able to. You don't need that. Yeah. Now, do y'all know about like natural logs and e's? Like how those are friends? Have you done that in the math class before? Yeah. So, you know, the natural log of e is 1. And if you ever have something, like in this case right here, in this situation, if we're solving for the concentration of A, this is the same thing as saying the natural log of X. To make that natural log go away, we're going to take this side of the equation and we're going to make it an exponent of E. I may need to just, do you have this written down? Can I borrow somebody's paper?
No, it's all written down.
It's all written down. I think it might be helpful. Do I need to take a second and put this e to this, brings that down for you, and then you have this to raise to the e? Do you want me to do that? Yeah. All right. Let me see if I can. If it's all written down, then I should have it right here. It's not written down. Well, I can't like make that work. Let me get my little marker. See what I can squeeze in the side for you. If you want to, I'll tell you what, if you'll just write down from here up, are y'all okay with filling in this part? Okay, so write down from here up, and then I'll take it from here on the other screen, okay? And I'll write it down. And I may just turn it over. Yeah, I might actually do that. Oh, I found hold on the other sheet. I know, everybody hates this, right? Who likes this? Nobody. 0 people like natural logs. I actually went to the math teacher today and I said, you know, is there a magical way to tell people that, you know, they're inverse functions and that they cancel each other out? Is there like a better way to say that? And they said, no, that's exactly how we say it. And I was just like, I bet if I taught that, I would come up with a magical way to say it better.
What, you and natural log?
I mean, yeah, I mean, I know how to do this, but like I said, it's just, I don't like saying, oh, it's just this. I don't like that. Okay. I'm gonna take it from the top up here. Y'all are giving me that look. I see the look. Does it look like, really, Miss Freeman? I see it. So, yeah, you're giving me the look. Let's just start with this formula on here, because that's how, yeah, I see the look. I'm gonna make you feel better, okay? Don't stop giving me the look. Let's just start over. Take the formula from the formula sheet. Can you tell which one it is? It's first order. Can you tell? And then let's just write that down. I left out a part. So far, so good? Are you, okay, so far, so good. Now, I am solving for the concentration at 500 seconds. So that's this guy. That guy at 500 seconds. I'm solving for that. So I want to isolate this, And I'm going to do that by moving this to the other side. So the natural log of the concentration at 500 seconds. Y'all know that this little 500 down here doesn't mean anything. That means absolutely nothing. That just says I'm referring to the concentration at 500 seconds. This doesn't mean anything mathematically. I don't have to like make that 500 go away. I'm just labeling it. You okay so far? All right. Is equal to, well, y'all know what K was, right? It was that exponent number, like 0.003 something. What was it? 3 point? Was it a negative number?
It was 3. No. It was negative plus the negative right there. Okay.
So is, it was positive, but so I have negative K. So 3.3. Okay. And that was the negative number. Do we know what the time is? Do we know the change in time is at what time? 500. Okay, so we're looking, so this number times 500. Still good? All right. Now, remember, I am going to add this to this side. So plus the natural log at, yeah, so the initial concentration was that. And this little 0 means at the beginning. Does that make you feel like a little bit better? It's a little bit better. Okay. You can, in your calculator, you can simplify every little bit of this. And that's exactly what I would do first. So go ahead and hit your little buttons in your calculator and simplify the right-hand side. Yes, sir?
We're using units.
Sure. Yeah, and this is a second, and then this is first order, so this is second, -1. When you multiply those are about to go away. But yeah, sure. But yeah, okay, I gotta do this in my calculator. Am I in the way? I'm scared to write this. Watch my sig figs. I don't like to do sig figs until the end, so I'm not gonna do it. And I don't have a unit, it all canceled. Did you, that negative's kind of hanging out at the bottom. Let me, it's feeling a little low today. Is that what you got? Please tell me.
Yeah.
Ah, that's good. That's good. We're in this together, you guys. Okay? So it's not a change. So I have this number is equal to the natural log of A at 500 seconds. Now, I can't take the natural log of a number that I don't know. So when you are faced with this situation and you have to get the natural log to go away, what you end up doing is you have to raise e to the natural log of the constant. Like this is good, solid, what, algebra? Is this algebra class? I don't know. And then I have e to the negative 5.56. What ends up happening when you raise a natural log of a number to e, those cancel, okay? They're inverse operations. So then I have the concentration at 500 seconds, the natural log went away, is equal to e to negative 5.56. And you can totally hit e to the negative 5.56 in your calculator and get the number. E to the, hit the second button. So I got the concentration at 500 seconds is equal to 0.0038. Now let's just make sure that even makes sense. I start out with 0.02 molar and I end up with 0.0038 molar. That kind of makes sense, like I went down. Like if your number was bigger, probably screwed up. Yeah, okay. Is this what you got? Is that what the PowerPoint got? I guess we're about to find out, right? I'm like, oh, this popped up notes, that looks really pretty. I'll just go with that, but it ain't the same. It's not. Hey, is that what just happened?
Mm-hmm.
Yay! We win. Cool. That's as bad as it gets. That's it.
Good.
Yeah, that's it. That's as bad as it gets. Because 1 over a number, I can do that all day. You can figure out 1 over x. That's not a big deal. Alright, so, and it actually gets easier. In the next graph, that's why I marked out their mess. I'm like, you know what? No, there's no reason. I'm taking like a minute. Let's just take like a minute. We need to just party time. I'm not even reading that paragraph. I don't care. You know what? Natural log of the concentration, and I see that, that's my only reactant. AB is my only reactant. So overall first order reaction. Now, notice on these little graphs, they're always just for one reactant, right? So one reactant could have a straight line like this, and it's first order, and then another reactant could have a straight line, and it's 1 over the concentration, and that's second order. So we're just looking at one reactant at a time. All these cute little examples just have one reactant. How sweet. Thank you so much. So anyway, the whole paragraph just says that stuff is graphed out. I know it's a first order reaction. Now watch this mess. On that last example, it had natural log of the concentration, and then it had time, but it didn't have any numbers over here. It gave you a chart, right? Now this is great. We don't even need to really use all those crazy numbers on our calculator because they already figured out the natural log and put it here for us. So we didn't have to punch those buttons. If you punch those buttons with this, it ain't going to work out for you because they already did those. And your calculator will do that thing where it's like, we can't do that number in our calculator. That error syntax crap. Yeah, you know what I'm talking about. All right, so let's look at some more graphs. This is a good point to make. If the temperature is lower, then that means the reaction isn't going to go as fast, and so the slope of the line is going to be a little less steep. Are you okay with that? So the reaction is going to go a little bit slower, sorry. So like I said, first order reactions, when you just plot their concentration, if you just plot their molarity, their concentration over time, they are radioactive decay graph. Like that's radioactive decay, that is a first order reaction. You're looking at uranium or whatever. So anyway, and so the half-life is the time it takes the concentration of a reactant to decrease by half. Thank you, that's very deep. I like that sentence. That makes me feel like I'm home, okay? So anyway, and you can see that divided by 2 is 1 half-life, and see it's the same distance. The half-life is constant. So this is where I'm just like, forget you, crazy paper. No. So if we want to go ahead and find the half-life for the following reaction, I have here on my paper, I can actually find K. Do I have everything on here that I can find the rate constant? Do we have the initial concentration and a time? Oh, excuse me, an initial, yeah, that's what I meant to say. Do we have an initial concentration in time and a final concentration in time? With the natural logs of it. So what I want us to do is take your little formula sheet, okay, and you don't need to punch the natural log button in your calculator. If you look at the formula, I guess I could pull up that other screen, it's still there. Too much information. On your graph, what is that last time period at the end of the graph? Is it 600 or something?
Yeah.
All right, so if you take the natural log of the concentration, it's already there. They already told you it was like negative 4 point. Let's just do it. I got the graph. I got a graph right here. Let's just do it. Ready? Let's just fill it in. We don't need to use our calculator. They already did it for us. So the natural log at this final time was negative 4.93. So you need to be real careful when you're doing these. They may make it easier for you than you think. Minus the natural log of the concentration at the initial point, which is negative 3.91. Does your math teacher do that? When I went to school to learn how to be a math teacher for 12-year-olds, we did this thing.
Yep.
Do you do that? Is that a thing? Okay. That makes me happy. I like it. It's equal to negative K, and then there's like a random line. And then the time period was 600 seconds. So what you need to do is simplify that left-hand side by adding them together. And then I'm just going to divide both sides by negative 600. That'll take care of all my problems in the world. Let's see what I got. I like adding. I can do that. Adding is fun. Adding is fun. At negative 1.02. That was way easier than I needed to use. I didn't need to use a calculator for that. Is equal to negative K. I'm 600. Seconds. There you go. There's your seconds. So I'm going to divide both sides by 600 seconds. Negative 600 seconds. Well, I mean parentheses. Whatever that divided by negative 600 is. Still.
1.7.
And it's second to the negative first. And I saw the graph. Was the graph a first order reaction? So guess what? Your unit's going to have to be seconds to negative. So it turned out right. So we know we're good, right? So that's K. Now, this is where I mark through their bull mess stuff on their paper. Look, if you want to find, this is the third on your yellow paper, the last little formula is for half-life. CT sub half, yeah, that means half-life. If I want to find the half-life of this, do we have K? Well, yeah, we do. So if we want to find the half-life, all we have to do is take 0.693 divided by it.
So they redid that whole stuff just for that.
Yeah, and so here's the thing. In the notes this man made, like he has little notes and he'll put like, you know, like little side notes. And he says, on the AP exam, they aren't given 0.963, or yeah, 0.6, I'm looking at it upside down. 0.693 divided by K is a half-life, so you have to do it this way. Turns out you are given it, so yeah, we're not doing that. So this is the best way to do it, obviously. Much shorter. So anyway, it does take your... That took your calculator? Wow, okay. I'm sorry. I thought I had a pink calculator just like that.
But it's lighter.
No, I switched so I'd have a darker calculator. Are you sure that's not mine?
Oh.
I'll find mine. Mine's off with my keys in my pen.
I just thought you took mine.
Whatever. Anyway, so divide that out and let's find the half-life, okay? And this is going to be in seconds. So, I don't even know where that... Good, that's good. Go away. 40? 40 seconds?
400.
400 seconds?
There's 2.0s.
Oh.
What's the number?
400.
So it's 400.
7?
407. 0.6.
Oh, we don't need that in many significant figures. That's enough.
It's actually.
There. How do you feel that make you feel smart? That's as bad as it gets. Well, actually, that's less bad than that other thing. That's less bad than the other thing. Yes? The other thing was like, oh, I'm going to need to just do this myself. Are you okay, Cameron? Okay. I'm almost done talking, and then you get to practice the rest of the time. I don't have, like, yes. If it's half-life, it's got to be a time. Why is it inverse seconds, though, on this?
Yeah, like, cause
Oh, I know. I noticed that.
Seconds is on
Oh, because it's on the bottom and it's negative, so that brings it to the other side. Yeah, everything's fine. It's cool. It's right. Everything's right. Y'all are making me question the meaning of my life, like, oh, is that really right? It is fine. Okay, so if we look at that, did this go down? Oh, we can't tell if it went down by half because it's a natural log. Oh, never mind. I was like, oh, let's use our head. No, never mind. So we can do it this way. No, run away. No, run away. Which of the following processes has the shorter half-life? And then justify your answer. The higher the rate constant, the shorter the half-life. Because you're multiplying this by the concentration and getting the rate, right? Okay, stop. Stop freaking out. If I'm trying to find the rate, right? The higher this number is, the higher the reaction rate. And the faster the reaction's going, the shorter the half-life's going to be. I mean, y'all good there? Do y'all have to write something down? Sure. The bigger this number is, then the higher the rate's going to be. So the faster the reaction's going to be going. Well, if something has a half-life of 10 billion years versus 10 seconds, which one's going faster? Sure. So the higher the rate constant, the faster the reaction. Yes?
You just justify it with that formula saying that the bigger the number on the bottom.
Yeah, let's do that. I've run trial for life. Good. Yes, but yeah, that works too. So, okay. Thanks, Drew. I'm going to retire now since y'all got it. Some of y'all in calculus, y'all can teach this later. Oh, look, there's the answer. Both processes are first order. Process 1 happens at a faster rate when they have the same initial concentrations, and it has a higher magnitude on the rate constant, which is kind of what I was saying there. So don't freak out. We already did this. We drew a fraction at the beginning of class, and it had 2 numbers. So when you see 1 over a number, look at me in the face. Everything's fine. This is the same thing we just did. It's the same formula, except that instead of having a natural log, you got the concentration on the bottom of a 1. Is this not the same exact formula? It is. It's fine. Everything's fine. And just ignore those red letters. Everything's fine. And so, yeah, we can rearrange it. And when we rearrange it, y equals mx plus b, it makes a straight line. Okay, that's not a newsflash to you because I already showed you that it makes a straight line. And there's a straight line. So if you have a reaction and 1 over the concentration gives you a straight line, then second order. Now notice on those first 2, the lines had a negative slope. This doesn't have a negative slope. And the reason why it doesn't have a negative slope is an inverse, right? And so this concentration over time is going to get smaller. And so the smaller this number gets, I'm actually going to get a bigger number out, right? 1 divided by 100 versus 1 divided by 10 versus 1 divided by 1. I'm getting a bigger number each time. That's the one. This is the only one that makes a positive line. Do I need to write that down for you? Do you want me to write some numbers under 1? Write some numbers under 1? Sure. Let's do some numbers in our calculator, sure. Let's give like some real numbers that actually could be molarities. Let's just do like 1 over 0.2 molar, 1 over 0.1 molar, and then 1 over 0.05 molar. And these are legitimate molarities over the course of a reaction. So just enter those numbers into your calculator. I stopped class to do this. Do it. 1 divided by 0.2. Look, $1 divided by 20 cents is 5. I don't need a calculator for that. So 5 and then 10, and then $1 divided by 5 cents is 20. You see how that is? Yeah. 7th grade right here. I'm afraid. Anyway, so that gives me 5 and then 10 and then 20. And so if I'm graphing this number over time, then I'm going to have, 5, 10, 15, 20. So it's going to go up. As the concentration of the reactants go down, which is what happens in chemistry, stuff runs out. Unless you're at equilibrium, and that's the next chapter, it's going to be fine. But yeah, so the inverse of it goes up. So you're dividing by a smaller number. Whee! Math, that is fun. Okay, how you feeling? Feeling good? Still feeling okay. It's like, I hate this. We're almost done. Hey, look, this is the stuff that AP exams are made of right here. Look, they're going to give you, and this is one of your free response. It's going to give you, what? Okay, so I'm not talking. they're going to give you a bunch of graphs, and then you're going to have to look at them, and they might give you 3 graphs, and then which one makes a straight line, right? Well, is natural log and the concentration making a straight line? Is this a straight line? No, so it's not first order. And then 1 over it makes a straight line, and that line's going up. Okay, this is a second order. Okay, so this reaction is second order in respect to nitrogen dioxide. Do I need these numbers? At this point in my life to determine the order, do I need these numbers? You just need that graph, and you need to know what an M&M looks like, and what an L looks like, and then a fraction has 2 numbers. Okay. I feel like, I'll work this one out for you, but I bet that you could go ahead and do this. Do you feel like you can do it? You're like, no, Miss Freeman, you do it. Let's see what they got. All right, so we know it's a second order reaction because it makes a straight line. NO2 is the only reactant, so I know it's second overall. The rate law, we did this yesterday. You still feeling pretty good? If it's second order, you put a 2 up there. Still feeling good about that? Is the rate law on your paper? Do you need to write it down then? Probably. It's second order because the graph of 1 over the concentration makes a straight line. And so remember when you draw a fraction, you have to draw 2 numbers.
Yeah.
So if it's, and notice,
I was getting confused because the coefficient.
the coefficients don't mean jack ever. 0 times does that mean anything. You can never, ever tell the rate law of an experiment from the coefficients. You can, once you know the rate of one thing, you can compare the rate of something else with a coefficient. But you can't ever determine the rate law from the coefficients, and then we'll use that to try to trick you. This was purely coincidence that we're both 2, okay? All right, so we're going to use t equals 0 and some other time. This is the formula on your paper, on your yellow paper. Do you see the formula on your yellow paper? Can you find that? That's the formula for second order. They don't tell you it's second order, but we know it is because we have fractions and you write 2 things. So go ahead and write that down. I'm feeling good about that. Hey, is there a negative sign in front of the KT? Why not? Because the slope's positive, not necessary. Y'all, we're making this so easy. Y'all really need to get me a good Christmas present. I'm serious. It's gonna be fun. I don't like when they do that. They throw all the stuff in here. So this is the concentration at what time did they use for 0.1? 10 seconds. So at 10 seconds, the molarity is 0.015. Just kidding. No, that is right. At 10 seconds, the polarity, molarity, whatever. The molarity is 0.015, and the initial concentration was this. And then, in your calculator, see if you can make this work in your calculator. I challenge you to a calculator off. So this is the answer. This is this thing here. What happened? Oh, okay. Yeah. I see what they're doing. Maybe I see what they're doing. Oh, yeah. This is just 100. This is just 100 seconds. I gotta do that thing. Do I have to do the thing? I gotta do the thing. Do I have to just clear the screen and do my own thing? Are you sure? They're dividing both sides by 100 because it was the time at 100. I got it. Look at that. You got it? Cool. Now look at the units. It's the second order. The M's going to have 1 less, and it's going to be the, I guess, inverse. It's going to be the negative of it. So second order, you're going to have 1 less on the M, and it's going to have a negative in front of it, and they always have second minus 1. How you feel about that? How do I get rid of those 2 M's right there? Oh, when you're subtracting, you're still just gonna have one M. Like saying, I got 12 eggs minus 2 eggs, I got 10 eggs, still got just one thing of eggs. I think the way I explained it was pretty good. Okay, so yeah. Oh, and if you heat it up or you speed it up, then the rate becomes faster. Then the line is gonna have a greater or a steeper slope, and that's gonna segue us in nicely into the next topic, which is how fast things go and why. Well, I guess that's okay. We did it. So you have 35 minutes to do these practice problems. We do need one about graphs to put on the sticky note things. Let's pick one together. Let's do number
2.
on number 2. It doesn't have. Oh, it says first order. How nice. I think 2 is really good. Let's do 2.
I didn't even look at it, I just saw the graph.
2 is good, but it doesn't have the units. But I was like, no. I cooked on the lab for tomorrow today during my planning time, and it made me mad. Like, Jada, when you came in, like, I know I was looking pretty mad. Like, it wasn't you. Like, I did not enjoy it, and I didn't like it, and it made me mad. And I don't like it. I don't like it. I don't even know if I want to do it. I don't know. Do you want to just do it and see what happens, and we can just be mad together? It has little micro